Hey guys, so I want to follow up on the video I just did recently on methanol injection. So I just filled the tank up with methanol, 100% concentration. I'm going to take it for a test drive. I've wrote down the atmospheric conditions right now, temperature, humidity, pressure, all the things. And we're going to go do a test drive. And once I get it up to temperature, I'll do a hit and I'll see if I can put that on video. And just a quick little hit, we'll see what temperature drops to and what the temperature delta is between what my IET sensor says and what temperature is outside, and then we'll see what the temperature drops is, and we'll do the calculation and we'll see if our math that I'm telling you so accurate is actually accurate. So stay tuned. Hey guys, so I just got done with both the runs. I did 2 runs and got some data, and we're going to go over the data log real quick and some math, and we'll prove everything that I talked about in that other video is correct and almost exact. So I'm going to turn the light off here to make it a little easier. Alright, so the run you just saw is this run right here, okay? You can tell in the video how I kind of feathered the gas a little bit, and we got up here, you know, we're at, that's 2000 RPM, and then you can see this is where the torque converter kind of flashes. I'm going to turn a couple of things on here and talk about them. So this is boost pressure down here, okay? The average is 4.8 pounds throughout the entire run, was about 4.8 pounds. But at the peak, which is where we're doing our calculations, the peaks are 5.9 pounds of boost, and that's just like right in here. It's kind of the average for the last little bit here. And that's where we're going to see our largest temperature drop. So this blue line is our intake air temperature. So we're starting over here at 146 degrees, okay? That's before the meth hit. So as soon as boost comes in and the meth gets triggered, you can see obviously the bottom falls out of it. So this is 146 degrees at the start, and I think we dropped down here, the lowest was 102, but it's basically kind of down here, 102, 103. Alright, so we did our math based off of what the maximum temperature drop is. And it kind of flatlines. It gets pretty close and then just kind of hangs out here. And I can tell you right here, this part and this part, this whole area here, you're cooling off the blower casing. And I will prove that here in just a minute. We talked about that in that other video, but I thought it was perfect today. I wanted to do 2 runs back to back, and I wanted to show that the first run's not going to show as much of a temperature drop as the second run, and I'm going to prove that. I did 2 runs back to back. There's the first one here, and the second one is right here, okay? It was a little shorter. I cut it off just right before the 8th mile mark, but I just wanted to show, and I don't know, I was just data logging. I wasn't focused on the data, and I can just prove to you, and we're gonna go over that here in just a minute. But let's first start our video off here. Let me get this. It's hard to hold this phone and do this at the same time. I want to get the whole thing, the whole run in here. All right, here, it's easier just to do it this way. All right, so we got the video. I'm gonna turn the lights back on. So the red line is obviously RPM. We took it up to, I think I took it up to about 6850, so almost 6900 RPM. And we're gonna talk about the math here. So first thing, the temperature outside, the Draggy said it was 88 degrees. The weather service said it was 90 degrees outside. My manifold air temperature sensor said 87, so that's what we're going with. The pressure today was 29.97 inches of water, which is 14.72 psia, and the humidity today was 53% whenever I did the run. We had a big storm coming in, so this was right before that hit. And then, so first thing you have to do is calculate air density. So I did a video on this, so I'm not going to go a lot into it, but the first thing you need to do before you can calculate the air density is get your partial pressure. Okay, you got to get it for the ambient and then post blower for the manifold. Okay, so this is how you can tell this delta density here. You can see if you're actually generating more power, because if you're more dense here, you're going to generate more horsepower. So if you keep turning the blower faster and faster and faster and faster, this bottom number here, this 1.352 and this 0.6356, these are a table lookup. You can just look up the table, and it's based off of whatever your temperature is. So if the discharge temperature of the blower, this is ambient, so 0.6356, that's psia. That's based off 87 degrees Fahrenheit. So type in 87 degrees Fahrenheit and it'll tell you what your partial pressure is. It's a calculation, or you can look at the table. This is based off 146 degrees. That's what we started our run at, was 146 degrees. So 1.352 psia. Okay. The faster you spin the blower, the higher this number is going to go. Okay, and this isn't the part that's where you're talking about air density. Air density is down here, and if your air density is still higher than ambient, you are gonna make more horsepower. You can turn the blower fast enough to where this number starts going down. Okay, and we'll talk about that in a minute. But anyway, so the pre-blower, so I did a table lookup. 87 degrees Fahrenheit is 0.63. You multiply that by 53% relative humidity, so that's 0.53. That gives you your psia, and you have to subtract this down here. So this is our actual air density calculation. I did a whole video on this, so I'm not going to get into it. You can go back and watch that video on air density, or I think it's titled How to Calculate Horsepower Potential Based on Atmospheric Conditions. But anyway, so 14.72 psia is just what ambient pressure was. You got to subtract your partial pressure from that, okay? And then you multiply that by 144, divide that by 53.5, and again, these numbers and what they mean are on that air density video, so like I said, I'm not wasting time with that. Multiply that by our outside air temperature, and you got to put that in absolute scale, so this is to 459.67 is to go to Rankine, okay? So the ambient air density today is lower than J1349. It's 0.0708 pounds per cubic foot. Okay, so this next one is in the manifold. This is post blower inside the manifold. Okay, I even wrote it there. Manifold air density. Look at that. So 14.72, 5.9 is the max boost. Now I understand the average here. If we were to drag this, let me grab my mouse here, and we just drag it from here to here. Okay, that's the whole run. And we hit this little button right here that says update the stats, and then I click on boost anywhere. The average is 4.8 psig. Okay, ignore this max and minimum because obviously it's the sniper throttle body. The sensor on it is obviously not very good, so you have to go off the average. You can't take these peaks and valleys. You've got to pick the average. So the 5.9 comes in like right in here. So we're talking about 67 to 6800 RPM, this average. Okay, but let me get back at the swollen out here. And the reason that we're picking the max boost is because that's where we're going to see the maximum impact on the methanol. So, alright. So, now we've calculated our air densities, 0.098 pounds per cubic foot in the manifold. So that is a significantly higher air density than atmospheric. That means the blower is not inefficient. We are currently making the boost right now at 4.8 pounds or 5.9 pounds, unless that blower is currently not inefficient. Now, I'll show you in a minute. I'll show you a data log on my 10 pounds of boost. Yes, it's still faster. It's not a whole lot faster, but it is faster. It's still got a higher air density, but you will see that the blower is getting way inefficient because the methanol can't even turn temperature, and I'll show you that in a minute. So we've calculated density. Okay, this you've got to add the boost. So 14.72 plus the boost minus your partial pressure, which is calculated right here based off subtracting 1.352. Well, you're multiplying it here, but you're subtracting this number. All that number is, and I went into this on the air density video, was that's the amount of air pressure that's because of water, the grains of water, however you want to put it, the moisture in the air, that is displacing, so you have to subtract it. It's not, you can't use that for your calculation. Okay, so alright, so the first thing I want to do is, if you do not have an IET sensor, you don't have a way to measure what the actual IETs are, I'm going to prove to you that that calculation I gave you is extremely close. Okay, so this is the formula I gave you on the last video, the one just before this one. And if you calculate it out, 87, you got to do absolute scale, you do your partial pressure, or not partial pressure, your ambient pressure plus your boost divided by atmospheric pressure, raise it to gamma. Well, it's 1 minus 1 over gamma. And then once you do this, you multiply it by the denominator here to get T2, which is 142.26 degrees Fahrenheit. So this should be how high the temperature gets. If you look here, it was 146. Like right here before we started, it was 145, 146, pretty stable. That's very close, okay? That's very close to this number. So now we got to find our BTUs an hour on the discharge of the blower. How many BTUs an hour we're generating with the blower, downstream of the blower. So that's the last video, delta T times CFM times 0.24 times 60 times air density. So we've got our delta T. This is the actual delta T. I'm not using this yet. I'll show you. I'll do the same calculation using our calculated number, but this was actual. This is what the IET sensor showed as our delta T. And then this, I went over the last video. This is 192 cubic inch blower divided by 12 cubed. This is my blower speed, 67 tooth divided by 41 tooth. And then we went up to 6,800, just a little above 6,800 RPM. And then 0.098 is the air density inside the manifold, because this is downstream of the blower, so you got to use that density number. So that's 102,801 BTUs an hour. Now, temperature drop with 24 gallons per hour of 100% methanol. Now again, this is my nozzle sizes. Your nozzle sizes might be smaller than that, they might be bigger than that. I don't know. Make sure you use your nozzle size. And that last video, I went over all the methanol injection, how to do that. So I'm not going over it in this video. 24 gallons per hour times 6.52. That's just how much it weighs, times the BTUs it removes, BTUs, and then divide by our 102,801 BTUs an hour. Okay, I'm not going over the details of all this math because I did it in the last video. Multiply that by our delta T. 39.96 degrees is how much we should expect for a temperature drop. What did we see? The actual temperature drop went from 146 degrees down to 112. Now, that was going up here, okay, down here. And this 87 degrees, this yellow line here is my manifold air temperature. Let me just show you that. 87 degrees. Bloop. So, if you look down here, it was at 81 degrees. I had just pulled the truck out and got it up to temperature a little bit and just started data logging right away. Okay, and you can see it's pretty stable. And then whenever we open the throttle blades wide open, it started getting constant airflow. You see this nice little trend up. Well, there's nothing that's going to heat up that air because of the way I have my manifold designed. And so you're getting up here to 87, so from 81 to 87, but 87 is how hot it was outside. So the tube, the air filters, the plenum, all the things were still pretty chill. They weren't quite up to atmospheric temperature yet. But when you had the throttle blade wide open and you just full sent it, that temperature sensor got up to what the actual temperature is outside. Okay, and then it just kind of stayed there. A little bled off a little bit, but it was pretty much stayed there. So I'll take that out of here. Don't want too many things open at the same time. And we can take boost out. Just get it just IATs and RPMs. So now that's 39. The actual was 34. And I can tell you right now, the reason we didn't get as much temperature drop as we expected based on our calculation is because we are cooling off. We're using some of that methanol to cool the rotors and the blower casing off. Okay? And I can prove it. This is cooling the blower casing. Because what I did, these runs are only separated by like 4 or 5 minutes. I literally just went around a turn and then got on an off ramp. And here's the other run. Okay, and I'm gonna get that zoomed in a little bit better here. So we went from 145 degrees, okay, 145 degrees IATs, and we went, I'm gonna refresh this little button. It just basically refreshes all this data up here, averages and minimum and maximums. The minimum was 102 degrees. Alright, so we went all the way down. That other one, when we were on that first gear run, we only got to 134 degree temperature drop. Here we're already at 118. Then we shift into second, and we get all the way down here to 102. And if you notice, it was still on its way down as RPMs were going up. It still went down, and I don't know how much lower it would have went. It looks like it's kind of, if you look at this steep hill and it's slowly kind of rounding off, it probably was getting pretty close to as low as it's going to go. But 102 degrees. So if you look at that run, 145 minus 102, that's 43 degrees. Our calculated was 39.96 degrees. That's only 3 degrees off of our mathematical calculation of what we should see. The other one was 34. So that was 5.96 degrees less cooling than we expected to get. And then we cool the blower casing off on that round 1. And then the run 2, I say round 1, run 1. And then run 2, 4 minutes later, less than 4 minutes later, it's like 4 minutes later roughly, just went around a curve and then stopped and then went again. We got 3 degrees more cooling than we calculated. So I can tell you, we were cooling the blower casing off on that first run from just sitting there idle, heat soaking. until I came to a stop at the freeway. Okay, so the second run, you just watch it just falls, the bottom falls out of it. And it was still going down a little bit, so we may have even got even more cooling. But again, it looks like it's rounding off, so I think it's pretty much done right there at 102 degrees. It looks like it's rounding off. And then you can just see it immediately goes back up when the throttle blade closes and the methanol stops injecting. I mean, you can see it's literally as soon, let me turn boost back on here. Turn boost back on, you can see as soon as boost goes away, methanol goes away, and temperatures start going right back up. So, you know, I wanted to show you guys that the math that I showed you is exactly what it did. Okay, you got to get your air density. Once you know your air density, if you don't have an IET sensor, I'm just proving a point to you with this video that that is an accurate representation of what you should expect inside the plenum. And just to prove that point even more, let's go down here to this little square. Using calculated IET data, which is the 142.26 and not the 146 that I actually read on the sensor. You do all the same math, okay? The only thing you're replacing is the delta T here. You get 96,000 BTUs an hour versus 102. That seems less. Well, what's the temperature drop? Well, look at this. This is divided by 96,284, and then we're multiplying it by the delta T here. But instead of the delta T being 146 minus 87, it's 142.26 minus 87, 39.96. Wait a minute. It's the exact same amount of temperature drop. It's the same. Okay? No difference. You can do the math for yourself. You're going to get the same numbers. Okay? So whether you have an IET sensor or not, you can still do this. You can still figure out how much temperature drop you should expect so that you can look at that and go, okay, I can get away with this much timing. I can get away with this much timing, okay? Now again, this is the maximum. Obviously, you got to build your timing curve based on what the temperature is at each one of the RPM ranges. You can go in here if you have one of these snipers or one of the more advanced versions. You can go in here to fuel flow. That's fuel pressure. Hold on. Where did I go? Here it is. I'm trying to look at the phone instead of just looking at the computer. And you can actually go in here and go, okay, I'm at 24 gallons an hour. Okay, I'm pumping 184 pound-hour at 3,500 RPM. And then you can put that point in there, and you can plot this entire graph, which I have done in Excel, and I can tell you what octane I have, and tell you exactly what my octane is at every RPM range under certain boost conditions. I have the same thing for my 10 pound of boost pulley. This one's like 4.8 on average, but it, you know, right at between 6,700 RPM to 6,900 RPM, it's basically 5.9 pounds. And in this video, I'm gonna go open a different data log. This was my first time running 10 pounds of boost with the 24 gallon per hour nozzle. Okay, and if you look at this, this is 10 pounds. You can see that's 9.7 pounds, and I just picked a random point, but you can see it's kind of in the middle there. So you're about 10 pounds of boost. And if we let's turn the boost off, turn that off. Let's just do manifold air temperature and blower IETs, and let's get it on scale, because I just had a much lower scale here a minute ago. Let's go see, we're at 160 there. let's get it on scale here. Okay, so here's where you can see the blower is inefficient as all get out. Okay, the blower speed has went up. Okay, but temperature started off at idle at 163 degrees. And then from, what's that, 1500 RPM up to 6846 RPM. And the first, just one first gear pull, okay, because I let off here. One first gear pull, which is about 70 miles an hour roughly, 60, 70 miles an hour. You can see that temperatures are just climbing. The methanol is not touching it. It is, I mean, you're still getting that cooling. This would have been a much steeper curve. It would be about 40 degrees hotter. So at the peak, we're at like 206 degrees intake air temperature. Okay, 206 degrees, that's getting really dangerous on getting advanced timing, because I think even with 10 pounds of boost, I started with 100 octane. So even with 100 octane, my fuel flow, I was only at 103 octane. So you can only get so aggressive with the timing on 10 pounds of boost with 103 octane. You just can't with this kind of temperature. Now, if you had enough water methanol to get this down to 100 degrees Fahrenheit, you could get even more aggressive with the timing. That's why people start adding water, because water, it cools more. Again, we talked about in the last video that mathematically it cools more. You may not see it in your IAT sensor. Like, I will add water to this at some point and show you guys when I have time, but you may not see it, and we talked about the reasons why in that last video, so I'm not going to rehash that. But I just want to show you that the blower is inefficient. The methanol versus my 5 pounds of boost, 5 pounds of boost, you can actually see temperature just plummet, versus 10 pounds of boost, just 5 more pounds, and temperature is just on a steady incline, and it's just going to the moon. And if I wouldn't have let off here, it would have just kept going up, and we start getting to the detonation area. Now, even with this temperature up like this, that kills air density, but it is a couple tenths faster. I mean, in this video I just showed you before I started this discussion, temperatures were, let's see, I mean, I think the run itself, again, that was like the first run on the 24 gallons an hour, so the tune's still not dialed in. It'll get a little faster, and I also didn't have a really good launch, but regardless, it did, I think, like a 12.9 second quarter mile. I think it can get in the mid to low 12s on that 5 pounds of boost if I get the tune right and the suspension and all that set up correctly. But I wanted to do a comparison on the 5 pounds of boost and watch temperature drop and do the math and then show you here, okay, what 10 pounds will look like. Hopefully that was helpful. If you stay on the video, I'll just show you a video of whenever I pulled up, of the engine itself idling, and a couple nice little whacks so you can hear the beautiful sound that is a Root supercharger. I mean, it's just a beautiful sound. They're not very good compressors. I could get 10 pounds of boost on an intercooled turbo and probably make another 100, 200 horsepower, and it's just because of air density and efficiency. The parasitic loss, you turn the blower faster to get this 10 pounds of boost. I'm here pointing and you can see what I'm pointing at, but you do 10 pounds of boost, well, your parasitic drag on the engine, you're losing horsepower to turn it that fast, and it's not gaining you enough air density. I think the difference between my 10 pounds and 5 pounds is a few tenths. I think it was like 2 or 3 miles an hour at the 8th mile. I think at the 8th mile it does 90 miles an hour on the 10 pounds of boost, and on this it was like 80 something, 88, I don't remember, miles an hour. And 1.8 0.85 second 60 foot versus a 1.93 or whatever it was 60 foot. I mean, it's within a couple tenths. It's not even that crazy. And I bet when I dial in this one, it'll be very close to the same speed. The 10 pounds of boost, I can run an 8-second flat, 8th mile, and on this it did like a 8, I don't know, 8.5, 8.6, 8.8, something like that. It was significantly higher, but I haven't dialed this tune in. That other one I had dialed in. So again, you turn the blower faster, it does not always make more horsepower. Makes maybe a little bit, but you get to a point of no return and you start getting into detonation. Like on this, I'm on 93 octane. I can run that thing on 93 octane with the methanol, and I still have very high octane. I think I'm at like right at 100 octane at max fuel flow at 6,800 RPM worth of octane between 93 octane mixed with the methanol. So you can't beat it. It's not worth the extra to get the 100 octane and then put the methanol in there just for a couple of tenths, unless you're at the racetrack trying to do a bracket race and you are trying to set a certain speed. But anyway, I have another pulley that's kind of right in the middle ground, so I'll run it when I have some time. It makes about 8 pounds. It's kind of between the two, and we'll see if it can keep up with the temperature with the methanol, and if it can. Where the point your blower is no longer efficient is when you can no longer maintain temperature with your injection. So if the methanol, if you start injecting the methanol and temperature does what it did on the 5 pounds of boost and starts going down, excellent. If it stays the same under methanol, excellent. You're right there on the borderline of efficiency of that blower. As soon as the temperature does what it's doing on this 10 pounds and it just starts climbing, and no matter what you do, it's not turning, time to add water. And be careful with your timing, and be careful with how much starting octane you have. And again, I can put my 13 pound pulley on there, but it's not going to be any faster unless I can get control of temperature. And again, you put water on there and get control of temperature, and you can put timing to it, but the water doesn't burn and it doesn't facilitate making horsepower. So there's a path of no return where you can keep cooling it to the point where you start misfiring in the cylinders, but you're not making any more horsepower. I run 100% methanol for a reason. It facilitates horsepower. So as soon as I start adding water, I'll do it and I'll see what times go to, but the draggy will tell me if the times aren't getting faster, it's not making more horsepower. So anyway, I just wanted to practice what I preach on here and show you guys that I'm not full of garbage. This is factual information that you can take to the bank and you can use it on your hot rod. That's it. That's all I got, guys. And I'll put this in this video with a couple supercharger whacks. I love it. Hopefully you like it. See ya.